Unit 2, Homework 3, we're looking at buffers and activities. So my first question, the molar solubility of calcium hydroxide increases from something to something in the presence of a 0.1 molar KNO3 solution. And then we're given the Ksp value. Well, I thought it would be easier if I did this instead of write it all out. So first, we need to find the molar solubility of the compound, ignoring the activities. We set that up the same way you've seen before. We take our calcium hydroxide and split it into its constituent ions. We know that the calcium concentration will be represented by X, and then because of our stoichiometry, the concentration of our hydroxide will be represented by 2X. We can then set up that Ksp equation. Ksp is going to be equal to the concentration of the calcium times, it looks like I dropped a squared, but the concentration of the hydroxide squared. That's what that 2 is supposed to mean. Then we fill in the numbers we have. So we have the Ksp. This is supposed to be a squared here. We have that Ksp, and we have X and 2X. Now, the most common mistake I see students make is not squaring this 2. So this ends up being 4x cubed because we have our x here and then x squared here. So that's how we get our 4x cubed. Divide both sides by 4 and then take the cube root, and you should get x is equal to 0.0118. So the molar solubility will increase from our initial 118, our initial molar solubility that we just found, to some value we need to find now. So now we need to take into account the activities of the activity coefficients, the activities of our ions. So if our Ksp, our true Ksp then, is going to be equal to the activity of the calcium times the concentration of the calcium times the activity of the hydroxide squared times the concentration of hydroxide squared. Whatever we're doing to our concentration in the Ksp equation, we also need to be doing to the activity. What that means is if we're squaring our hydroxide ion concentration, we need to square that activity coefficient as well. Now, we have to calculate these activity coefficients, and we're going to start with the ionic strength of the solution if we assume that the calcium hydroxide is only going to have a negligible contribution to the ionic strength. Because after all, it has very little solubility. That's our solid that we're measuring with Ksp. So we have to look at our activity coefficient. We have to find the ionic strength based on that potassium nitrate. So the concentration of the potassium nitrate was 0.100 molar. Now this is KNO3. KNO3, when it breaks up, it has a K that has a 1 plus, and it has a nitrate, which is a 1 minus. We need the charge, and we need the concentration of each of those items. So the ionic strength, which is mu, is going to be equal to 1/2 times, and then we have our parentheses, the concentration of our cation times the charge of our cation squared, the concentration of our anion times the charge of our anion squared. Now, because it's all 1-to-1 stoichiometry with potassium nitrate, we have 1 squared for each of our charges. So our ionic strength is actually equal to 0.1 molar. Now we have to look up our activity coefficients. So under resources, under activities, it's probably under activity coefficient. This is where we're going to find no, it's not. Where is our table? Here's our table. So ionic strength is 0.1. So we need to go over to the right. We're going to be reading this right-hand column. And we need to find the activity coefficient for our calcium and our hydroxide. Calcium is a +2. It's located here in the middle. So all the way on the right, that activity coefficient is 0.40. And here I have 0.405. This is the value given by Harris, but this is the value from our OER text. OH minus is, that's the fourth row down. So we need to read the activity coefficient all the way over on the right with the ionic strength that matches, so 0.76, and that is the same. So we have now the Ksp value, which did not change. These tabulated values that we found on our resources. And now we need to substitute x and 2x for our concentrations. So it's a similar, this would be x and this would be 2x. It's a similar procedure from here forward. We've just added in the activity coefficients. So now it's just algebra. We take our 0.405, multiply it by 0.76 squared, and then divide both sides by that value. And then, I forgot about the 4. So we have our 2 squared value as well that has to be taken into account. Then we're working algebra here so that our x value, which is our molar solubility, is now 0.0191 molar. So in the homework then, we would put 0.0191 molar. So in the presence of inert ions, or this inert ionic solution, the molar solubility would increase from 0.0118 to 0.0191. Question 2, we're asked to interpolate to find the activity coefficient of calcium in a solution of 0.0027 molar calcium chloride. So 0.007 molar CaCl2. And we're looking for the activity coefficient of calcium. So we need to calculate the ionic strength. Then we can interpolate. So the ionic strength mu is going to be 1/2 the concentration of the calcium times the charge of the calcium squared plus the concentration of the chlorine, like that, times its charge, which is a -1, squared. So what is the concentration of each of these things? Well, I'm going to do this the long way because I want to make sure that this is abundantly clear. We have 0.0027 moles of calcium chloride per 1 liter of calcium chloride. Now, when calcium chloride breaks into pieces, it breaks into its calcium and 2 chloride ions. So the concentration of our calcium, 1 mole of CaCl2 has 1 mole of Ca2+ that it will produce. So the concentration of our calcium then will be 0.0027 moles per liter. Now the concentration of our chlorine is going to be different than that, and that is because of the stoichiometry involved. Here's my balanced chemical equation. I have a 2 there. So the concentration of the chlorine is going to be 2 times the concentration of the calcium. So I have 0.0054. Now I do expect your values to be different. And this bit that's added in as some sort of feedback that you'll get after you turn in your homework, that is sample data. It's not necessarily the data that you have in your question. So now I can calculate this ionic strength. And I get a mu value of 0.0081. That is my ionic strength. Now I'm going to need to interpolate, it says so, I'm going to need to interpolate the activity coefficient of calcium at this ionic strength. So I need to find my bounds over here. I need to find my calcium. And calcium is down here in the middle, I believe. We just had it, yeah. And I need to find what ionic strengths are on either side or would bookend this ionic strength of 0.008. And the answer is my ionic strength bookends would be 0.005 and 0.01. You see how my value would be in between them. Now the activity coefficient for calcium at both of these ionic strengths is also used in our calculation. So I need to bring that data in. So I have 0.749 for my first one, and it's 0.675 for my second one. So I know my gamma, the gamma I'm looking for, is somewhere between these two numbers. Actually, I have my alligators going the wrong way, but it is somewhere between these two numbers nonetheless. And that's what we're finding when we're interpolating, is we're finding where is it between those two numbers. And we are assuming linearity. So we have our unknown activity coefficient interval. So I'm going to pick that I will have this as my first value. So 0.749 minus the gamma I'm looking for, divided by the delta of our activity coefficient. So 0.749 minus 0.675. Now I need the sample ionic strength interval. So I'm going to put it in the same order, 0.005 minus 0.0081. And I know that's going to give me a negative value. That's okay. They will all work out in the end. And then I have my known ionic strength. So I'm going to use these values, 0.005 minus 0.01. And now all I have to do is solve for this gamma. So I'm going to stop and start the video so you'll see things just kind of appear, but I will give you each of the pieces and you can check your work as you go. So I get a calculated activity coefficient then of 0.703 for these conditions. My question number 3 is a titration. We have a 25 milliliter sample of imidazole, and we're titrating it with a strong acid. So we have a weak base and a strong acid. So what's the pH of the solution at 10.26 milliliters of strong acid added? Well, first let's find out where are we in this titration. So I start with my volume of imidazole, which is a base, and I'm going to multiply it by the concentration, 5,000. That's moles per liter. This is, imidazole is a 1-to-1. It has one acidic hydrogen, so 1 mole of imidazole will be neutralized by 1 mole of acid. And we are working with nitric acid, which is monoprotic. So I'm just going to skip a step basically and equate it to 1 mole of HNO3. And I have, let's see, 0.1361 moles of acid per liter. So this will give me the equivalence point. This will tell me what my equivalence volume is for this particular situation. 361. And the equivalence volume then is 0.00918. Now the units for that's liters. So the equivalence volume is 9.18 milliliters. I am past the equivalence point, or the equivalence volume. So what is the pH going to be dependent on? The pH is going to be dependent on the excess acid. So imidazole plus acid reacts to form protonated imidazole and nitrate. So we have used up all of our imidazole and we have extra nitric acid. How much extra nitric acid do we have? Well, 10.26 milliliters minus 9.18 milliliters. And this is a deviation from the problem solving that I did within the lecture. And I'm doing this intentionally in case you've seen this method before. If you don't like this method, if this method bothers you in any particular way, then go back to the original method. That's okay. And so let's find out how many moles of acid we have left over. So I take the original molarity per milliliter. There are 1,000 milliliters in a liter, so 1.08 times 0.1361 divided by 1,000. Then I have an excess of 0.123146988. Now that's moles of acid left over, but I have to know what my total volume is. So the total volume is 10.26 milliliters of the acid plus 25 milliliters of the base. I have 0.03526 liters that I need to divide those moles by. in order to get the new concentration. So the concentration of my hydrogen ion, because I am using a strong acid, is 4.168, and it keeps going, but I'm just going to leave it in my calculator, times 10 to the negative third, capital M molar. The question asked us for the pH. So we need to take the negative log of this value, and I get 2.38. Now, I do expect your values to be different for this question, so make sure you are calculating for your question. Number four, I'm going to ask you to explain to me what these things mean. So we're shown a portion of a titration curve. The first derivative graph and the second derivative graph are shown. So explain the information that can be determined. Well, this is directly from the information provided within the classroom. And I wanted to make sure to call your attention to it because I don't know if you're going to need it for the lab, but this is an important piece of information depending on where you're going with this whole analytical chemistry thing. So here, derivatives of titration curves is the explanation of what the derivatives of the titration curves mean. In fact, here's the graphs that are provided in the homework assignment. So in the first derivative graph, there is a peak, and that peak is the equivalence point of the titration. So the X value is going to be the equivalence volume. The second derivative graph shows the equivalence point at the X-axis crossing. That's where you find the equivalence for the second derivative. So from either of those graphs, you should be able to find the equivalence volume, but you should also be able to determine what that pKa is, because the pKa is going to be equal to the pH at the half equivalence volume. So that's one of those titration things that you have to know. And that's something that could be explained for the titration curve. Number 5, we have imidazole again. We have a different concentration of nitric acid, and we're asked for the pH of the solution. So whenever you're presented with a question like this, you should determine where in the titration are you. Before anything is added, before the equivalence point, at the equivalence point, or after the equivalence point. So I'm going to venture a guess that we are before the equivalence point. Now we should do that calculation real quick just to be sure. So this setup yields 7.67 milliliters of HNO3 in order to achieve the equivalence point. So the equivalence volume of this particular titration is 7.67 milliliters. We are definitely before that equivalence point. So we're going to set up our equation. We have imidazole, which is a base, and it's going to react with the acid of our strong acid base. We're going to have a little bit of an equilibrium occur, and we're going to end up with this protonated imidazole. Well, how much and what's going on here? So let's look at the moles. Let's shift with moles. 0.025 times 0.05 in order to get how many moles of imidazole we start with. I have 6.25 times 10 to the negative 4. Now, and that's moles. So for the hydrogen ion, because I'm adding a strong acid, 0.00334, 0.1629, I have 5.44 times 10 to the negative 4 moles of that hydrogen ion that I'm adding. So I'm going to be taking those moles away from the imidazole, and I'm going to be adding those moles to the protonated imidazole. Now, when I do that, I end up using all of these moles, so that goes to 0. So I have 8.09 times 10 to the negative 5th moles left. I have no H plus left, but I do have 5.44 times 10 to the negative 4th moles of the protonated imidazole. Now, at this point, we need to analyze. Can we use the Henderson-Hasselbalch here? And I don't believe we can, because Well, I was about to say because our moles are less than 3 times different than our Ka value, but it's not that we need to compare. It's actually the molarity. And the molarity, if I take these moles and divide by 0.028, I get something times 10 to the negative third. And that does match our rule of 1,000. So it does look like we should be able to use the Henderson-Hasselbalch here. So pH equals pKa plus the log log of the base, 8.09 times 10 to the negative fifth, divided by the acid, 5.44 times 10 to the negative fourth. The pKa of imidazole, let's see, I'm going to go back over here to my resources, my Ka table, and imidazole is listed here as 6.993. So now I should just be able to do some algebra and figure out my new pH. And I end up with a new pH of 6.1. I get 6.5, and then it continues. So I would actually round that up to 6.7. So I would enter 6.17. This is another situation where I do expect your numbers to be different. Number 6, assuming complete dissociation of the salt, calculate the ionic strength of a 0.08 molar solution of magnesium chloride. Well, ionic strength is mu, and that's going to be 1/2 the concentration of the cation times the charge of the cation squared plus the concentration of the anion times the charge of the anion squared. So now what are these concentrations? Well, the magnesium, if we're assuming complete dissociation, the magnesium is going to be 1:1. So the concentration of magnesium is 0.08. The concentration of the chlorine, on the other hand, is 2 times that, so 0.16. So I get an ionic strength, a mu value of 0.24. Number 7, use complete sentences. Explain the difference between a primary and a secondary standard used in titrations. With a question like this, I expect you to be able to define both primary and secondary, and then tell me how do they differ. Because a primary standard is a compound that can be weighed with reliability. A secondary standard, you can't, because it's usually needs to be back titrated, or the reason it's secondary is it has to be secondarily analyzed. Then give me some examples of primary standards and secondary standards. And I would love for you to be able to tell me when it would be most useful to use one versus the other, but that might be pushing it, and I'm aware of that. And then my last problem, a 20 milliliter sample of imidazole. So here we go with imidazole again. 20 milliliter sample of 0.0512 m imidazole, titrated with my strong acid again. So 1 mole of imidazole, 1 mole of HNO3. I'm looking at 0.1 mole per liter. We have 10 milliliters, so 1,000 milliliters there. Are we at the equivalence point? 0.02 times 0.05 times 1,000 divided by 0.1. Well, the equivalence volume is 10.00 milliliters, so we are at the equivalence point. Now, if you don't remember how to calculate with the equivalence point, part of what I wanted to do here is to show you how to find these things. So come over here to titration calculations. We're looking for strong and weak. So that was strong, weak acid and strong base, or strong acid and weak base. And that's what we're looking at. So we are at the equivalence point. So I'm going to go here. So the moles of the acid equal the moles of the base. Okay. So I need to set up the equation. So what's happening here is the imidazole is reacting with the strong acid, and it is all going to protonated imidazole. Okay, we have none here and it's all here. So how much is all of this? Well, let's find out how many moles, 0.05. So we have protonated imidazole at 1.00 times 10 to the negative 3 moles. That's my starting point. Now it is going to be in equilibrium and it is in an aqueous solution. And what we're going to do is end up forming hydronium ion and imidazole anion. But with what values? So I need to divide these moles by the total volume. The total volume here is 30 milliliters because what we're going to end up doing is setting up a Ka. So my Ka expression will be the concentration of the hydronium ion times the concentration of the imidazole divided by the concentration of the protonated imidazole. So I do need this concentration. And this concentration works out to be 0.033, and that repeats, capital M, molar. So we're going to shift this equilibrium. It will shift by some amount x. So my Ka becomes x squared over 0.03000 minus x. But what is that Ka value? Well, I'm going to come back up here to my Ka table of values, and I have imidazole. I have the pKa. Remember how to find a Ka from a pKa. The pKa is 6.993, or was it given to me? It was given to me, and I ignored it. So we don't have to do that. The Ka is 1.02 times 10 to the negative 7, and I should pay more attention. So can we simplify this? And the answer is yes, because we are more than 1,000 times different. So I can simplify this, and this becomes x squared over 0.03000 equals 1.02 times 10 to the negative 7. Nope, no, that's a 3 repeating. I did that wrong. That's a 3 repeating. That needs to be the concentration, not the total volume. So that value, still in my calculator, times 1.02 times 10 to the negative 7. So we end up with x squared equals 3.4 times 10 to the negative 9. So x is equal to 5.83 times 10 to the negative 5th. So this is where we stop and go, but what does x represent? Well, x represents the concentration of the hydronium ion. And because it represents the concentration of the hydronium ion, I can just take the log of that value and find that the pH, which is what we were looking for, the pH is 4.23 at this point. So I do expect your values to be different on a problem like that, but reach out if